Hey there, and welcome. Today, we are stepping right into the molecular workshop. We're going to look at how chemists actually build things. And specifically, we're exploring two really essential blueprints for creating a class of molecules called halides. These things are crucial. They're the starting points for making everything from life-saving drugs to plastics. Okay, let's get right into it. So, let's start with the biggest question of all. How do you even build a new molecule? It's easy to think of chemistry as just studying stuff that's already out there, but a huge part of it, maybe the most exciting part, is about creation. It's kind of like being a molecular architect, designing and building brand new structures literally from the atom up. And a major strategy in that whole construction game is substitution. It's all about swapping one piece of a molecule for another. And that is exactly our focus today. Our goal? It's simple. We're going to learn two really powerful ways to create halides using this exact strategy. Now, before we start building, we should probably know what we're making, right? So what is a halide? Well, it's just an organic compound where one of those superstar atoms from the halogen group, fluorine, chlorine, bromine, or iodine, is attached to a carbon atom. The best way to think of them is like universal adapters in a molecular toolkit. They let us connect all sorts of different chemical pieces together. Super useful. Okay, so for any substitution to actually happen, one group has to leave to make room for the new one coming in. And this brings us to a really fundamental concept. I like to call it the art of a good exit. In chemistry, we call it the leaving group. You will hear this phrase in pretty much every organic chemistry lab on the planet. And it really drives the point home. See, if the group that's supposed to leave is, well, clingy and unstable, your reaction is just not going to work. It's going nowhere. You absolutely need a group that is stable and perfectly happy to leave all on its own. And this slide illustrates the idea perfectly. Take the hydroxyl group, the OH- you find in alcohols. On its own, it's a terrible leaving group. Just awful. It's unstable, it doesn't want to go. But if you add an acid, you can protonate it, which is just a fancy way of saying you stick an extra proton on it, and it turns into OH2+. And what's OH2+? H2O. It's just water. And water is an incredibly stable, very happy to leave group. It's like you've given it a golden ticket to exit the reaction. No fuss, no problem. All right, with that crucial idea of leaving groups in our back pocket, let's look at our first blueprint. This is a classic method for turning really common molecules, alcohols, into these super versatile alkyl halides. So it's this really clean two-step process. First, just like we saw, you use an acid to upgrade that lousy OH group into the excellent OH2+ leaving group. Then, for step 2, the halide you want to add, let's say it's a bromide ion, it just swoops in, kicks out that water molecule, and takes its place. Boom. Simple, elegant, and it works like a charm. Now, here's where it gets really interesting. The shape of the alcohol actually changes the entire game plan. For simpler, less crowded alcohols, the halide attacks at the exact same time the water leaves. It's like a perfectly choreographed one-step swap. But for bigger, bulkier alcohols, there's just no room for that to happen. So instead, the water has to leave first. This creates a temporary, positively charged carbon center. Then, and only then, can the halide come in and attach. So it's the same end goal, but a totally different path, all because of a little molecular crowding. And of course, chemists always have more than one trick up their sleeve. Those acids aren't the only tools for the job. There's a whole toolbox of other reagents, things like phosphorus trichloride or thionyl chloride, that can also get this alcohol to halide conversion done, and sometimes they're even more efficient. Okay, time for our second blueprint. This one is for building a different kind of halide. We're moving on from simple chains and turning our attention to those stable aromatic rings. We're going to look at a famous and really powerful method called the Sandmeyer reaction. You can think of the Sandmeyer reaction as a precision instrument. It's designed for one very specific task, adding a halogen onto an aromatic ring to create something called an aryl halide. Now, these rings are famously stable and unreactive, so you need a pretty special approach to modify them. So here's the magic. The Sandmeyer reaction starts with a molecule that has an absolutely fantastic leaving group already built right in. It's called a diazonium group, N2+. And why is it so great? Well, think about it. When N2 leaves, it becomes nitrogen gas, which just bubbles away out of your reaction, gone forever. You can't get a better leaving group than one that literally vanishes. And just look at the kind of precision this gives you.
You start with the exact same material in both cases. If you use a copper chloride reagent, bam, you get chlorobenzene. But if you just swap that out for a copper cyanide reagent, you get cyanobenzene instead. The tool you choose directly and reliably determines what you build. It is an incredibly controlled way to do chemistry.
Okay, so let's put our two blueprints right next to each other and just quickly recap the key differences. So here's the whole story at a glance. Pathway 1 is our go-to for making alkyl halides, and it's all about taking an alcohol with a bad leaving group and making it better. Pathway 2, the Sandmeyer reaction, that's our special tool for making aryl halides, and its power comes from having an amazing pre-installed leaving group right from the start. Two different problems, two totally brilliant chemical solutions. So there you have it. We've just mastered the blueprints for making these incredibly important halides. But here's the real excitement. These molecules, they aren't the end of the story. They're the beginning. They're the starting materials for building countless other more complex, more amazing structures. Which really just leaves us with one final, exciting question. Now that we know how to build them, what are we going to create next?